when I was in college, my electromagnetism professor told us that. He was an interesting character. So we're in section 10.4, and we're going to talk about polar coordinates. Now, the first part of this is probably going to be review. It's stuff that you've seen in several different contexts, and then hopefully what I plan to do is kind of take it maybe a little further than you've done before. So let's just define what we mean by polar coordinates. So we have our axes, our x-axis here is called our polar axis. And then we're interested in a directed segment to a point. And theta is the angle between our segment and the polar axis. And we'll call this the origin. And the length of our segment is r. And we define this point P as has the coordinates r and theta. So this will uniquely define, well, not uniquely define, but it will define a point in space. We call the origin in polar coordinates, the origin is called the pole. The polar axis corresponds to theta equals 0. And r is our distance from O to P. So from the origin to our point. And theta is the angle between the polar axis and our segment OP. And we're moving, theta we define as moving counterclockwise. I'm going to say CCW. So this is how we define our coordinates, and this is something that we've all seen before. Polar coordinates are not a unique representation like the rectangular coordinates. We can add any multiple of 2 pi to our angle and get back to the same point, or we can also have a negative radius and add a multiple of pi to our angle. So our radius can be negative, and we can add a multiple of pi to our angle, and we get to the same point. And the pole is the pole is 0 theta for any theta. So if our radius is 0 for any angle, we're at the pole. So again, mostly review stuff that we've all seen before. A couple of things that we're going to be interested in doing that, and we're going to use as a tool is coordinate conversion. We're going to convert between polar coordinates and rectangular coordinates. We'll also end up converting between polar and cylindrical, polar and spherical. So we'll do all kinds of coordinate conversion. And again, mostly stuff that you've seen before. So let's go over this quickly. So we just want to be able to switch back and forth between coordinates, and we'll end up using these tools when we talk about equations in polar coordinates. So I'm going to overlay our polar coordinates on our rectangular coordinates. And that went backwards. So here's our x and y axis. And we'll put our directed segment for our polar coordinates. And we're at point P here. And P is our theta, and it's also, we can represent it as x and y. And here's our theta. And this distance is x, and this distance is y on a right triangle. So let's remember our coordinate conversions. So if we want to represent x, how do we represent x in terms of our polar coordinates? X is our cosine theta. We've all seen this a bunch of times. Y is r sine theta. How do we find our angle? Inverse tangent, so I'm going to say tangent theta is y over x. And our radius, what's our relationship for our radius with x and y? R is the square root of x squared plus y squared, or r squared equals x squared plus y squared. And this is true, these are true for any r. So these are the formulas that we use for our coordinate conversions. So let's do a couple of let's practice a little bit just to get back into using polar coordinates. Let's do some conversions. So if we have our theta is 2 pi over 6, we want to convert to rectangular coordinates. So x is going to be 2 cosine pi over 6, which equals 2 times cosine of pi over 6. We remember? Square root of 3 over 2. So x is just square root of 3. And y equals 2 sine pi over 6, which is 2 times the sine of pi over 6. 1/2. So y would be 1. So our point in rectangular coordinates would just be square root of 3, 1. Now sometimes when we go the other way, we have to pay attention to some signs. We have to figure out the signs of our coordinates, give us some information about our quadrants. So let's look at an example of that. So we want to go from xy to r theta, where xy is -1 square root 3. So what quadrant are we in here? We're in the second quadrant. The -1 here tells us we're in the second quadrant, so we have to pay attention to that when we're finding our angle. So we're in the second quadrant. Tangent theta, we want to find our angle. Tangent theta is negative square root of 3 over 1, which is just negative square root of 3. So theta in the second quadrant where tangent is negative square root of 3. We remember? 2 pi over 3. So theta is 2 pi over 3 in the second quadrant. And this is for our angle is in the second quadrant, so this would be for r greater than 0. If we wanted to use a negative r, then we could use a different angle. What angle could we use if we wanted to use a negative r? What is it, Lee? Negative pi thirds. So just pi units away. So r equals negative pi thirds for r less than 0. And r, we said r squared is x squared plus y squared. So in our case, r would be the square root of 1 plus 3, which would be 2. So we have a couple of choices here for our representation. So r theta, we could say is 2 pi over 3, or negative 2 negative pi over 3. And we can have any multiples, 2 pi multiples. We can add multiples of 2 pi to these angles to get additional points. So our representations aren't unique. So questions on this? Pretty, again, mostly review, stuff we've seen before. Now things start getting interesting when we start talking about graphs. That's what we're going to be interested in, is graphs of polar equations. We're going to talk about tangent lines. We're going to talk about area. We're going to talk about all the surface area of revolution. We're going to talk about arc length. So we're interested in graphs, and to me, that's really where polar coordinates get fun. So polar graphs. And that book that I was showing you is full of graphs of polar equations. So a couple of ways that we can figure out graphs of polar equations. We can to graph polar equations by hand is kind of difficult. The book goes through an explanation where you're constructing a table of values and plotting points. But what we're going to do in this class, for the most part, is I say thank goodness for technology, because we have calculators that will graph our polar equations nicely. So when we need a graph, when we need to visualize what a polar equation, what a curve is going to look like, a graph of a polar equation, we're going to be using our calculator. But it's also beneficial, it's also useful to know how to convert between a polar representation and a rectangular representation, and also start becoming familiar with how the graph of a particular polar equation looks like. So I want to start just by asking some questions about what these graphs look like without using our calculator, just thinking about what the graph is telling us, what the information is telling us. So let's convert to rectangular coordinates. So the first one is r equals a, where a is some constant. What would this be in rectangular coordinates? So a is just a constant. So someone set a line. What do you say, Griff? A circle. So line, circle, anybody else? So let's say we had, let me give you a more concrete example. What if we had r equals 4. But saying the radius equals 4 for any theta. That's going to be a circle. So this is a circle. So I'm going to erase this, and this is a circle with radius A. The next one, a little trickier. Theta equals pi over 6. What is it, Lee? Lee says this one's a line. Do we agree? I see a couple of nods. How would we tell for sure? Anybody have an idea of how we would analytically verify that this is a line? What's our conversion for between rectangular and polar when we have theta? Tangent. So we could say tangent of theta, tangent of pi over 6 equals y over x. So this tells us that y over x equals square root of 3 over 3, and y equals square root of 3 over 3x. So that is definitely a line. And the slope is just the tangent of our angle. So the slope is square root of 3 over 3. So a line through the origin with slope square root of 3 over 3. Even a little more tricky. R equals secant theta. We probably need to do some conversions here. Does anybody have an idea what this might be? No? Close. So, all right, how'd you come up with that?
Because 1 over cosine, so you multiply by cosine, you get our cosine theta equals 1.
Okay,
Our
so
cosine theta equals x.
okay, so x. So what Cole is saying is x equals our cosine theta. That's our conversion, right? R is secant theta. So if we substitute secant theta in for r, I get x equals secant theta cosine theta, and that just equals 1. So this would just be the line x equals 1. So we just used our conversion, substituted secant theta in for r, and we got x equals 1. So that's a line, another line. So starting to become familiar with some of these equations is a good thing when we're talking about polar and rectangular. So again, when we actually have to plot an equation, a polar equation, use your calculator. One thing to be aware of is that the curve may be traced multiple times in the interval between 0 and 2 pi. So when you graph, you want to make sure on what interval your curve is traced a single time. So between 0 and 2 pi, your curve can be traced over multiple times. And if you're in doubt, double check, plug in some points so that you're sure you're graphing your equations, or that you're looking at the interval that you're interested in. In your book, on page, let me find the page. They give a chart with a bunch of graphs of polar equations. What's that? 735. So I would say not necessarily to memorize those, but be a little bit familiar with some of these graphs, especially the rose curves and the circles. Those come up frequently. The limasones and the cardioids come up fairly frequently. So it's not that you need to memorize those, but just look over that chart. As we do more, you'll see these repeatedly, and you should start becoming more familiar. Just like we know what y equals x squared looks like, you know what y equals sine of x looks like. You'll start to recognize what if we have a rose curve, or if we have a circle, you'll recognize that fairly quickly. So what I want to do just for the rest of a little bit of this of the notes is just practice a little bit converting between polar and rectangular. So just practice on some conversion, so you can see a few tricks that you might end up having to use. So we're just going to do some conversions. So the first one, we have r squared cosine theta sine theta equals 4. And we want to convert this to rectangular coordinates. So what would we do? So Eric says, let's rewrite this as r cosine theta, r sine theta equals 4. And that changes, we can convert that to xy equals 4. And what is this graph? 4 over x. And what does it look like? What do we call those kinds of graphs? It's an inverse function, or it looks like this, and it has asymptotes, right? It's a hyperbola. This is a hyperbola. And the axis is rotated 45 degrees. So this is a hyperbola. Next one, r equals 1 plus 2r cosine theta. What do you think we're going to do with this one? We have this r here and we have this r here. That makes it kind of tricky. Anybody have any suggestions on a procedure? No ideas? Yeah.
I was just thinking you plug in the square root of x squared plus y squared for r, and then you plug in x for r.
Okay. So Griff says let's plug in square root of x squared plus y squared for r, and that equals 1 plus 2 times x. So this would work. I was going to do it in a slightly different order, but this is essentially what I was going to do. Now, if we wanted to make this look a little nicer, what are we going to do? Square both sides. So I get x squared plus y squared equals, when I square this, I get 1 plus 4x plus 4x squared. And then I can gather everything on one side of the equation if I wanted to. If I rearrange this, I should get, I get y squared minus 3x squared minus 4x minus 1 equals 0. And if we wanted to carry this further out, if we wanted to come up with a kind of a standard rectangular equation, do you know what we do from here? Think back to pre-calc. Someone said it. Complete the square, so we'd complete the square for x, we'd complete the square for y, and this, I think, would come out to maybe be an ellipse or maybe a hyperbola. Just looking at it, I'm not sure for sure. So we'd complete the square, and we'd come up with a standard form for one of our conic sections. Let's look at a couple more, just a couple more here. R squared equals 4r cosine theta. So this one I think is probably a little easier than the last one. So what would we do? How would we go about doing this one? Substitute. So what do we want to substitute? X squared plus y squared for r squared equals for x. So this one's not bad. We just gathering everything. X squared minus 4x plus y squared equals 0. Again, complete the square, and we end up with, if we complete the square, we have x minus 2 squared plus y squared equals 4, and we would have circle. So this is the equation of a circle. All right, one more. Let's look at D. R equals 4 over 2 cosine theta minus sine theta. What do we want to do here? Multiply both sides by the denominator. So I get r times 2 cosine theta minus sine theta equals 4. Then I distribute 2r cosine theta minus r sine theta equals 4. And I get 2x minus y equals 4. So sometimes polar coordinates are better, are an easier representation of our graph. Sometimes they're not. I would rather work with this than this. But either way we get a representation of what we're looking for. Questions on what we talked about? Yes?
How would you go about converting a spiral?
A spiral?
So what angle there?
So like r equals
Theta.
r equals theta.
Or you just have to say square root of x plus y squared.
What's that?
Or you just have to use inverse tangent.
I think you'd have to, I would say square root of x squared plus y squared equals inverse tangent of theta. And it's not a nice equation. Yeah, maybe you can look in there. I don't think they don't do conversions. They just show what the graph looks like. All right. Homework. Our favorite part, right?
Is it sectioned on the quiz or not?
I will double check. I think the quiz only goes through arc length and surface area with parametric equations.
Is the quiz calculator?
I can't remember. I'll look. Well, you need to know trig identities. So those are something, Lee, that having them memorized is a good thing. All right.